Okay, I'm Ed Mooring. I work for Xilinx, but I'm on assignment to Lenaro, and this is Ben Levinsky, who works for Xilinx. And we're going to talk about using RPMsg under OpenAMP for out-of-band transmission of large buffers. Now, how many of you know what out-of-band would refer to in this context? I'm a networking guy originally, so it's transmitting stuff not directly in the communication band, but alongside it. And that's the basic notion here. So the motivations: one, performance. Small fixed size buffers just don't work well for large streams of data. The use case we were originally looking at for this were things like radar, LiDAR, cameras, where there's a steady stream of large fixed size data elements. And they have, with the current RPMsg implementation, we have lots of small copies and lots of copies. And the other motivation was to take advantage of DMA-capable devices, because for a smart device, you could just tell the device to put the data into the buffer and then transmit the buffer, and you don't have to copy it at all on the transmitting end. And then the other motivation was community acceptance. People have proposed various zero-copy mechanisms for RPMsg and OpenAMP, and none of them seem to have gotten traction. And maybe this time it will, and maybe it's one of the other proposals, so this will spark some interest in one of the other proposals. This is a straw man. It's a proof of concept and a very basic outline of an architecture. It needs more work, but wanted to present it to see if there was enough interest to continue. So, requirements we were working under: zero copy of the payload, arbitrarily large buffers, but also adaptable to constrained memory environments, sender-managed resources, and compatible with the existing implementation. We didn't want to have to rewrite any existing code. So the basic architecture: you have a buffer pool, which is a chunk of contiguous physical memory shared between the two processors, distinct from RPMsg and VRing memory, and divided into fixed size buffers. And then there's a buffer management API that manages the buffers and per connection data. And here a connection is a single direction connection between two RPMsg endpoints. So the large data packets flow in only one direction. Again, this was based on the initial use case and keeping things simple and easy. And then there's a protocol to this that rides atop the existing RPMsg protocol. We take the unstructured payload of the RPMsg protocol and add a new header structure inside there. So it's transparent to the RPMsg implementation that there's the structure in there. There's a 32-bit out-of-band flag and type field, and then a type-dependent additional fields, each of 32 bits. It wastes some space, but is very convenient for processing and easy to understand, and you don't have to write code that takes into account alignment. And the various types specified so far are an init, which informs the receiver that the transmitter has got the connection started and what sort of resources are available. A data message, which has the index of a buffer and the length of the data, which is going to be less than or equal to the maximum size of the buffer. An acknowledgement, which is from the receiver when it's finished processing whatever data was in the buffer. And in-band data messages, which you have an unstructured data portion following and can be the only ones that can be sent in both directions. And the API, and this is, I've written out the API in more detail, but given the interests of the short time, this is a kind of high-level sketch. Buffers are passed as an index rather than an address. This is because in many of the environments we can think of, the shared memory region will have two different memory maps depending on the processor it's running on. One side might have a virtual memory, one might have a physical. It might actually be two different physical address ranges. And then buffer management APIs. Initialize a buffer pool, get a buffer, and put a buffer. There really doesn't need to be too much more than that. There's some sort of free list management because you obviously want to check to make sure you're not trying to put back a buffer that wasn't gotten, or get a buffer that's already in use, or you've already run out of buffers. And then message transmission. You send a buffer, send an in-band data message, and acknowledge a buffer. And atop that, you can implement more complex protocols and things with retransmissions and acknowledgements and back pressure / flow control. So here's what it looks like without zero copy. The APU application, APU and RPU, I don't know how specific to Xilinx there are. Think of it as an A53 or A72 and an R5 in our case. And that we're talking from the A series to the R series. So the APU writes something to the buffer, then sends it via RP message. The RP message library copies the buffer into the message. And then on the other end, the RP message library copies the message back. The RPU reads the buffer and then sends an acknowledgement. So there's a bit of copying and a number of steps. Now, if we go to a indirect method, the out-of-band method, the APU writes to the buffer, or in the ideal case, some smart device writes to the buffer and tells the APU when it's done. The APU sends the index via RP message. The RPU application reads the buffer at the index and sends an acknowledgement via RP message. So there's a little less copying and a few fewer steps. The other thing is that with this method, if, for instance, rather than another processor on the other end, it was something that could directly process this memory, like some form of custom logic on an FPGA, then you wouldn't even copy it at all. You'd operate directly on the buffer. And so this is not complete. Future things, crash reset / crash recovery, because right now we have no way of knowing if the sender crashed. The receiver has no way of knowing that it should probably ignore all the buffers that it has and start afresh. And ditto if the receiver crashes, the sender needs to know that it may not have gotten that data through and perform some sensible restart process. And then, because this is all very low level, there are probably higher level APIs that could be investigated once we know if anybody's interested in what people are interested in doing. For instance, an event-driven API to handle processing acknowledgements automatically and pass things off, things like that. And I believe with that, I'm turning the mic over to Ben for the actual implementation.
Thanks, Ed. So given Ed's architecture documents, I then fleshed out the initial proof of concept. And this has two parts. First is the Cortex R5 side, which receives the RP message callback and then processes the RP message, sees that it's an out-of-band RP message packet, translates the pointer into the shared memory space so that I can then read the data, and then after it sees that, then sends an ACK with the out-of-band packet back to the APU side. And then on the Cortex A53 side, there are a few parts. First is the out-of-band init message once it sets up the environment, as well as the out-of-band data messages to be sent. So on the R5 side, we have the new packet structure atop the RP message structure of the packet type that has the either init, data, etc. The shared buffer index, which is the index into the statically defined shared memory space between the A53 and the R5. And then it has the packet length, which is the amount of data after you have the base address into the shared memory space. And then on the R5 side, as we talked about, right, the process is it sees the packet, translates that into the shared memory space, and then once it processes it, sends the ACK back to the A53. On the A53 side, we have a comparison of the original RPMsg packet and the new packet. So we can see that there's the source address, the destination address, the reserved bits, length, flags, but then the payload is now, instead of actual data that was copied over, right, there could be no copy, right, if we have the LiDAR application, for example. Then we have the type, which is the init, data, so forth, the reference into the shared memory space, and how long that data is. So this is a diagram of the A53 side, what's going on. The step 1 write is optional. In this case, we implemented that because we're doing this all in software. And then once the data is written to the shared memory space, we then send the index over the RPMsg channel to the R5 and trigger the RPMsg callback. And then on the R5 side, parses it, sees that it's a data message, and then parses that into the shared memory space. Thanks.
I have maybe two questions. My first question is what the main difference between what you proposed and RDMA? And the second question is what advantage compared to the RDMA?
The virtue of this was that it is very simple and was quick to get people talking. And this is easy to implement. Something like RDMA might be a little more complicated, and it's a lot more flexible. So that would be a topic to look at. This isn't intended to be the final concept by any means. This is to get people talking and show that it can work. And particularly since, as Erwan's earlier talk, you could be running on something much more resource constrained, such as a Cortex-M series.
So for extremely resource-constrained devices, if you just want to do a data copy, right, and if you compare that to a VirtIO sort of mechanism, I'm not saying VirtIO is for data copy, I'm saying if you just take a data buffer and a kick, so is it capable of dialing down to that level on M3 type of devices? If you just want to do a single data copy across domains, say VM to VM or VM to hypervisors or something like that, or even across domains?
This particular one might be a little more complicated than if you're speaking of something like a simple double buffer operation.
Yes.
That's an even further simplification for a different environment. But we did explore that. But
is it in the plans?
Not in our plans at this moment.
So what's the advantage of passing the buffer IDs over buffer address?
If you have a different physical mapping of the shared memory region between the two sides, then you have to do some pointer swizzling every time you do this, and that's one more place you can indicate where you can make a mistake, where if you just have to multiply something, it's pretty easy to get it right.
So here you have a pool of buffer that you need to allocate. Can we imagine exporting buffer to your system? I mean, if I have a buffer coming from, I don't know, the display or the network stack, this is not a buffer that has been previously allocated via your API. So can I send this buffer via your API?
Unless the buffer was allocated from that shared memory pool, no. This is, again, a simplification. This is, again, keeping it as simple as possible
Yeah.
to prove something.
Okay.
So does there, each buffer has a, let's say, is it possible to have a different size or the fixed size?
The buffers are of a fixed length, and that's a maximum length, so you can send a shorter length field, but you're always going to use the same amount of buffer space.
So the buffer space is pre-allocated and cannot be used by other modules.
With this implementation, yes.
That looks like a disadvantage, you know.
It's an advantage in that it was easy to do.
Okay.
That brings up a further point. This is as lazy as I could be in thinking about it. So there are a lot of really good ideas out there, but I wanted to have something simple enough that I could present it in a short time and get reactions and maybe start some other people thinking.
So OpenAMP is a mechanism use RPMsg, your mechanism to transmit messages between the processors. Is this understanding correct?
Yes, this uses RPMsg under the hood as the kind of as a transport protocol.
What is the requirement on the networking controller? Let me assume you are transmitting between the two nodes using the, let me say, Ethernet. Okay. For example, the current RDMA require the NIC has some RDMA features. Right? For your implementation, you say you try to make it simple. What's your assumption of the underlying hardware support?
The underlying hardware support is shared memory and shared memory only. So it is between two cores, two different cores sharing the same sharing some of the same physical RAM. So it is purely a shared memory protocol. It is not a networking protocol exactly. So my comment about networking, it was perhaps a little misleading.
Okay, thank you.
Anyone else? Well, then thank you very much.